stacks available in sensors and software GPR systems. Stacking data 100 times reduces the noise level 10 times to 10% of the noise at one stack. Stacking the data 10,000 times reduces the noise 100 times to 1% of the noise at one stack. The effect of stacking is shown in this animation of a GPR line. In this example, the target is a flat metal plate buried 3 meters or 10 feet in the ground at the University of Arizona. Now, some of you know that Arizona's soil is generally not very good for deep GPR surveys. It tends to be very electrically conductive, which, as we know, attenuates GPR signals before they can travel very deep. But this example shows the power of stacking GPR data. At one stack, the depth of penetration is about 1.8 meters. But you'll see that by about 512 stacks, the depth of penetration is increased to about 3 meters, and we start to see the metal plate. Beyond that, by 1,024 or 2,048 stacks, we have a good image of the metal plate and lots of confidence that this is a real subsurface object. By stacking, the depth of penetration is increased more than 50%, which is significant if you're trying to detect every buried utility you can. Here's another example showing the same GPR line collected with 256 stacks on the left and 65,536 stacks on the right. Notice how the background noise is greatly reduced by stacking the data. At 256 stacks, we can see a hint of 3 hyperbolas that we would be gutsy and probably very uncomfortable to say are utilities. But at a higher number of stacks, the hyperbolas are so strong and obvious, we'd have no problem making that interpretation. So to get the most out of your GPR utility data, consider stacking more. Sensors and software systems make that easy. All you have to do is walk slower. That gives the GPR system the time it needs to stack the data more and increase the depth of penetration. Some of you may be familiar with the dark blue Dyna-Q bar plotted under GPR lines. The Dyna-Q bar is a color indication of how much the GPR trace above it has been stacked. Okay, now let's talk about gaining your GPR data. For most GPR operators, this is well known, but I mention it because I often see utility locators not spending the time necessary to gain their GPR data properly, and that can result in missing utilities in the data. As we mentioned, GPR signals get weaker with depth because of the attenuation or the absorption of the signal by the soil. The signals at the top of the GPR cross-section can be thousands of times stronger than the signals at the bottom. This means that GPR signals usually need to be gained or amplified, especially the weaker signals at depth. The gain we apply to the data is actually a ramp. So there's more amplification applied to the deeper, weaker signals than the shallower, stronger signals. After we apply gain, you can see that the deeper signals are stronger and more visible. So let's look at an example. Here you can see that while the image on the left looks like it might be okay, because we can see a hyperbola that could be a utility, when we apply more gain, we find that there's a second target that is deeper and weaker that we almost missed. It's important to realize that there is no perfect gain. If there was, we would not have an adjustable gain setting. We would just apply the perfect gain. The GPR signal attenuates at different rates in different soils at different locations. So gain is something that constantly gets adjusted throughout a GPR survey. A simple way of making sure that you've applied enough gain is that you should be able to see the random snowy signals from external radio sources at the bottom of the section. Once you can see that noise, you've usually applied